All right, let's dive right in. Today, we're stepping into the lab, but we're not just going to be chemists, we're going to be detectives. We're on a case, trying to uncover a hidden truth, a secret number that's literally invisible. So let's grab our metaphorical lab coats and start this investigation.
So picture this. You've got a beaker with a clear liquid in it, an acid, maybe. You know it's there, but you have absolutely no idea how strong it is. How concentrated is it really? It's a fundamental mystery. How on earth do you measure something you can't even see?
Well, the answer is one of the most elegant and honestly powerful techniques in a chemist's entire toolkit. It's called volumetric analysis. This is a method that lets us find the completely unknown by using something we know with incredible precision.
So, let's break it down. What exactly is this chemical mystery we're trying to solve? It's simple, really. We've got a solution with an unknown strength, a liquid holding a secret. And our mission, should we choose to accept it, is to find out its exact concentration. At its heart, volumetric analysis is basically a super-controlled chemical reaction. We take our mystery solution and we carefully react it with another solution, one whose concentration we know perfectly. By measuring exactly how much of that known solution it takes to finish the reaction, we can calculate the concentration of our unknown. It's chemical detective work, plain and simple.
Now, every good detective needs a reliable clue, right? A piece of evidence that is absolutely 100% trustworthy. In our case, that perfect clue is something called a standard solution.
A standard solution is our gold standard. It's our starting point, our one piece of solid truth. Its concentration, or molarity, is known with just incredible accuracy. And you gotta understand, without this perfectly known clue, all our other measurements would be totally meaningless. This clue has to be perfect.
So you might be wondering, okay, why all the fuss? Can't we just use some common chemical we have lying around the lab, like sodium hydroxide? And that is a great question, because the answer reveals something really fascinating about these chemicals.
And this is where our detective analogy gets really good. On the left, you've got your unreliable witness, sodium hydroxide. It's highly hygroscopic, which is just a fancy way of saying it loves to suck water right out of the air. So when you try to weigh it, you're also weighing a bunch of invisible water. That means its concentration is always changing. Totally unreliable. But on the right, we have our reliable clue, sodium carbonate. It's a pure, stable solid. You can weigh it out perfectly, which means you can create a standard solution that you can trust completely.
Okay, to do this kind of high-stakes, precision work, you can't just use any old beaker. Nope, you need a specialized toolkit, and each piece of equipment has one very, very specific job.
First up, we have the volumetric flask. This thing is a tool of extreme precision. It's designed for one job and one job only, to hold a single specific volume of liquid, like say 250.0 milliliters with incredible accuracy. This is how we make our perfectly reliable standard solution.
Next in the kit is the pipette. Its whole purpose in life is to transfer one single exact volume of our mystery solution into the flask where the interrogation is about to happen. This just ensures we're always working with the exact same amount of our unknown substance every time.
And finally, we have the star of the show, the burette. Now, unlike the other tools, this one is designed to deliver variable amounts of liquid, but still with super high precision. It lets us add our known solution drop by drop, carefully measuring the exact volume we've used. This is the instrument that lets us sneak up on that moment of truth.
All right, we've got our mystery, we've got our reliable clue, and we've got our toolkit. It's time. Let's bring them all together for the main event, the titration. This is the chemical interrogation where we finally force our unknown solution to reveal its secret.
So how does this interrogation go down? Well, first, we use our pipette to put a precise amount of the unknown stuff into a flask. Then, we add a few drops of an indicator. That's a special dye that's going to change color at just the right moment. Next, we slowly add our known solution from the burette, and we swirl that flask constantly to make sure everything's mixing. We keep going until, bam! The indicator flashes a new color and we stop. Immediately.
That instant, that sudden change of color, that's what we call the endpoint. It's the visual cue that tells us we've added just enough of our standard solution to react with all of the unknown substance in the flask. Not a drop more, not a drop less. That is our moment of truth.
And you know, while a simple color-changing indicator is the classic detective tool here, modern chemists have all sorts of other high-tech gadgets to find that endpoint. We can use a pH meter to spot a sudden jump in acidity, or a conductivity probe to find the point where electricity flows the least. We can even use a super-sensitive thermometer to find the exact peak temperature from the reaction's heat. All roads lead to that same moment of truth.
So, we've done the experiment. We've found our endpoint. We've carefully written down the volume from our burette. Now, it's time to do a little math and crack this case wide open.
This is where all the pieces of the puzzle just click into place. See, because we know the precise volume and concentration of our standard solution, we can figure out the exact amount of it we used. Chemists have a special unit for this. They call it a mole. The balanced chemical equation tells us the exact ratio these two chemicals react in. And with that ratio, a little bit of simple math is all it takes to reveal the concentration of our unknown.
And boom, the math leads us right here. For instance, in a typical experiment from our sources, after reacting a known solution with, say, 20 milliliters of our mystery acid, the calculation spits out the answer, 0.250 molar. The secret is out.
The case is cracked. We did it. We found the number. But you know what? Finding that single number, that's really just the beginning of the story.
So, why does this all matter? Well, this whole technique isn't just for finding one little number. It's a gateway to answering all kinds of amazing questions. We can use it to find out the purity of a medicine or the exact composition of a mixture. We can even use it to calculate the molar mass of a brand new compound or figure out exactly how many water molecules are trapped inside a crystal. It's an incredibly versatile tool for discovery.
Which I think leaves us with a pretty cool final thought. Volumetric analysis shows us how a logical process, combined with precise measurement, can reveal truths that are totally hidden from our senses. It really makes you wonder, doesn't it? What other invisible truths are all around us, just waiting for the right tool and the right detective to bring them to light?